is triple integrals. And to me, it just felt like integrals on steroids. And it's like, we did a single integral, we did a double integral. Now they're asking me to do triple integrals. They're like, what the heck, man? And they're talking about the fourth dimension and how is this applicable? Oh, it's applicable because the fourth dimension is time. And how are these surfaces? How are these volumes, right? Because a double integral was a volume. What the heck's a triple integral? Triple integral is something that's changing, is a lamina changing over time, and it's growing or expanding these volumes. Like how much did the volume expand? How much did the volume contract over time? And it has real life application to engineering and working with, you know, like hydraulics and fluid mechanics. And basically all of chapter 16 is going to be on fluid mechanics, because that is one of the, you know, prime applications of all this stuff is, you know, how do we use this in fluid dynamics? So 15.6 is triple integrals. Okay, triple integrals. Okay. So let's do this. A triple integral. Okay. The triple integral of f over the box B is the integral. So now our domain is no longer a area. Our domain is a box, a three-dimensional box. Okay. So instead of it being a rectangle for R, it's going to be a box now for B. Okay, B for box. Okay, B, f of x, y, z now. This is now a function of three variables. Okay, sometimes we call the fourth variable w. Okay, so this would be like a, you know, w is equal to f x, y, z. Okay, dv. Okay, dv, meaning that we're going to take the derivative with respect to the volume, right? Not the area, or not a line. Remember, dx was with respect to the line, dA was with respect to the area, and dv now is going to be with respect to the volume, right? So we're taking an integral over a volume. Again, some of this stuff is hard to conceptualize, and I get that, but the math is actually not too hard. Okay, so this is this. Okay, if f is continuous, on the rectangular box, box B. Okay, B, which we're going to say is going to be AB. So X goes from A to B, Y goes from C to D. Okay, and R goes from, okay, R to S. Sorry, Z goes from R to S, Y goes from C to D, and Z goes from R to S. So it's AB by CD by RS. Then, okay, then the triple integral over B, okay, of f of x, y, z, dv is equal to the triple integral from, okay, and I'm going to go in reverse order here, okay, just for the same reason that I went in reverse order last time. Well, it doesn't matter. The order doesn't matter. But it would be nice to end up with a function with regard, like like we want to kind of chop down one variable at a time, right? So I might do dz, dy, dx, right? And end up with x. Because then if I get rid of the z variable, then I'm just involved in with a function in terms of x and y. And if I get rid of the y variable, then I'm just end up with a function that involves x. Okay, but the order is not as important. Okay, so if we do z, then this is going to be r to s, y is going to be c to d, and x is going to be a to b. Okay, and this is f of x, y, z. Okay, okay, so that's how we set it up. Okay, our triple integral. Okay, so let's see how we do this guy. Okay, let's take example 1. Okay, let's find the triple integral over this box B. Okay, of B of x, y, z squared. Okay, dv. Okay, where b is equal to x, y, z, where x goes from 0 to 1. Okay, y goes from -1 to 2, and z goes from 0 to 3. Okay. Okay, so this is going to be x, y, z squared. Okay, so what I'm going to go in reverse order. It really doesn't matter that when we integrate over a box, it really doesn't matter what the order is. It depends on if we're going to have to do integration by parts, or if it's, you know, it's going to get real messy. This one's separable, so the order here doesn't really matter. But I'm going to do it in reverse order. dz, dy, dx. Okay, so z goes from 0 to 3. Okay, y goes from -1 to 2, and x goes from 0 to 1. Okay, so let's integrate this guy here. So this is going to be 2xyz evaluated from 0 to 3. Okay, integrate -1 to 2, integrate 0 to 1, dy dx. Okay, so this is going to be, plug in the 3 and the 0, this is going to be 2 times 3, which is 6. So this is 6xy now. Now it becomes a double integral, dy dx. Oh, okay. So this is 0 to 1, right? Yeah, 0 to 1. Okay, so now let's integrate with respect to, oops, did I do that wrong? I did that wrong. I'm dumb. I'm integrating, I'm not differentiating. This should be over 3. My bad. Okay, sorry about that. So plug in the 3, this becomes 9xy, right? Okay. Is that right? 9xy, right? So plug in the 3, plug in the 0. Okay. Yeah, integrating. Okay, so now let's integrate on with respect to y. So this becomes 9 halves xy squared, evaluated from -1 to 2, from 0 to 1 dx. Okay, cool. Okay, -1 to 2. Okay, so 0 to 3. 0 to 1, right? 0 to 1. And then this is going to be 9 halves. Okay, plug in for y. This is going to be x times 2 squared. okay, minus 9/2 x times -1 squared, okay, dx 0 to 1. Okay, so this is going to be 4 divided by 2 is 2. This is 18x minus 9/2. So 18 x minus 9/2 x. Okay. So this is going to be 36 minus 9, that's 27 halves x. Right, so 27 halves x. And I want to integrate that now from 0 to 1 dx. So this is going to be 27 halves. Boom, that's it. So this would be, oh no, this would be 27 fourths, sorry. Because this is x squared over 2. And then, sorry, it's x squared over 4 from 0 to 1, right? So plug in the 1, and I get 27 fourths. Okay, so that's number 1. Okay, triple integral. Okay, let's try number 2 here. Number 2, evaluate okay over a region. Okay, so we don't know, B is not necessarily, if I have E here, this is not a box. That's just over a region now. Just it could be a different type of shape. In this case, I believe it's a rectangle, or sorry, it's a tetrahedra. Okay, in this case, this is not a box. This is just a general volume. Okay, not a box. This is a general volume. Okay, this is a general volume. Okay. So this is going to be the triple integral z dv, okay, where E, okay, E is what? What are we integrating over? Okay, where E, what volume are we integrating over? Where E is the solid tetrahedron, bounded by the 4 planes x equals 0, y equals 0, z equals 0, and the plane x plus y plus z equals 1. Okay. Cool. Nice. Okay. So let's see how we can find our limits of integration here. Okay. So how are we going to find our limits of integration? Well, let's look at what is happening with this volume here. Okay. So we're bounded by, okay, what happens when you know, any two of these are 0. Any 2 equals 0, then the other one, then okay, then the intercepts, we call these intercepts, are equal to 1, right? Aren't they equal to 1? Aren't the intercepts equal to 1? So if we look at our graph, x, y, z, whoops, so x, y, z here. Okay, then wouldn't we get a point at 0, 1, 0? and a point at 0, 0, 1, and a point at 0, 0, or sorry, 1, 0, 0, and 0, 0, 1. Right? So wouldn't that be part of this plane? And that's the tetrahedron that we're talking about. We're talking about this tetrahedron that's bounded by these 4 planes here. Look at that. This tetrahedron, okay, think of it as a pyramid, but with 4 sides. Okay, tetrahedron is just a 4-sided pyramid. Okay, so this is going to be at the point 0, 1, 0. This is the point 1, 0, 0. Oops. 1, 0, 0. This is the point 0, 0, 1. Okay. Okay, and so this is the volume that I'm looking at. That's the volume that I'm looking at. Okay. So let's think about this for a second, right? We want a triple integral, okay, over the function z, okay, and I'm going to go dz, dy, dx. Okay. So what is z going to go from? What is z going to go from? Well, z goes from, say that we take a point here and we go to this point here. What would that point be? That would be on this plane. Let me try to highlight the plane that I'm talking about. I'm talking about this plane here, the slanted plane, right? So we'd have a point that goes, if we did a vertical slice here, let's do a vertical, like a vertical slice, then wouldn't it go from z equaling 0 to that plane, wherever that plane is, x, y, and z, right? So, but how could I rewrite this as a function of x and y in terms of z? Well, couldn't I just toss everything to the other side? Couldn't I just say that, you know, this is equivalent to z equals 1 minus x minus y? Right? So this becomes 1 minus x minus y. Okay. Cool, 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 cool. Okay, so now once we deal with that how that volume is created in the z direction, now let's talk about, well, what's happening in the x and y direction? What's happening with respect to y? Because once I integrate this, don't I get rid of that z variable? Isn't that z variable gone? All we have is in terms of x and y, which is a plane, which is the xy plane. And how does this thing behave in the xy plane? Well, let's make it another color here, a different color. XY plane. Okay, and so, well, this goes from, in the XY plane, this goes from 0, 1 to 1, 0, right? If we let Z be out of it, we don't have Z anymore. This is the XY plane. Then how would we do a double integral here? Well, a double integral, if we do dy dx, wouldn't that just be another vertical slice? That would be another vertical slice, but it's actually this slice here. It's that slice right there. Okay, does that make sense? It's the slice in the plane. Okay, that's the slice that I'm looking at, the slice of life. And so where does this go? Well, this goes from 0, okay, 0 y in the y direction, on y equals 0, to what? To this line, y equals what? Negative x plus 1. So this is y equals 1 minus x, right? So that's 1 minus x. Oh, okay. And then what does x go from in the line, on the number line, on the x-axis? What does x go from? Doesn't it just go from 0 to 1? Right? Doesn't that just go from 0 to 1? Maybe I'll put it in a different color code it. Okay, so what's a good one to put it in? I don't know. blue, we'll do blue. 0 to 1, right? So blue, 0 to 1. Okay, so what's that? That's this guy right here. That's this slice right here, 0 to 1, right? Okay, 0 to 1. Okay, does it make sense? Hopefully this makes sense. Okay, this is hopefully an easy enough example to make sense of how are you doing the triple integrals. And this is a lot to take in. It's a lot of dimensions to take in, right? So how do we do all these dimensions? How's this working? Right? So now let's integrate. Let's integrate this guy. Okay, so z, let's integrate on z. Okay, so z, that's going to be z squared over 2. Okay, from 0 to 1 minus x minus y. Okay, so this is going to be minus x minus y squared over 2. Okay, so this is now with respect to dy. Okay, maybe I'll keep it color coded here. dy goes from what? 0 to 1 minus x. Okay. Okay, so now I can integrate this. I could do a u du substitution if I wanted to. Erica, did you have a question? I think no? Okay, somebody's mic is on. Okay, sorry, I just saw that oh, it was yours. Okay, sorry, Long. Okay, no. Okay, for whatever reason, it's just not coming up with it. Like, oh, I get it. It's just because you're at the bottom of the list. Okay, it just showed that yours was not on. Okay, the people at the bottom of the list, it doesn't show that their mic is on for some reason. That's kind of dumb. Okay. Okay. Okay, so now, I mean, to me, this is kind of fun in a way. I mean, these are fun. This is like why I went into math. Like, this is just fun stuff for me. You're a freak of nature because you think triple integrals are fun. Like, oh, yep, you're right, I am. So that's why I have this job and you don't. So, yeah. Okay, so now let's do a UDU on this, right? UDU, okay, so we're only integrating with respect to y. So x in this case is a constant. We're going to treat x as a constant. Oh, okay. So what's u in this case? U is equal to 1 minus x minus y. What's du in this case? Well, isn't that just negative dy, right? Because x is a constant. Negative dy. Okay, so this is going to be negative du is equal to dy. Negative du equals dy. Okay, so this is going to be u squared over 2 negative du. Okay, I'm not going to change my limits of integration. I mean, I could if I really wanted to. Or I could just go back to the original variable at the end. Either way, you can change your limits if you want, or you can go back at the end to your original variable, which in this case was 1 minus x minus y. Either way you want to do it. Maybe I'll change them. Maybe I'll change them just for the heck of it. Okay. What happens when I plug in 1 minus x? It's actually not too bad. Because what happens when I plug in 1 minus x here? U of 1 minus x. Okay, if this is u of y, then this is 1 minus x minus 1 minus x. Well, isn't this just 0? Yeah, okay, that's kind of cool. So the top becomes 0. What about 0? Plug in 0 for y. 0 goes in for y, right? These both go in for y. Okay, u of 0, well, isn't that just 1 minus x minus 0, which is 1 minus x? Oh, okay. So it's almost like the limits got reversed. Okay, and I could reverse them back and do what? I could reverse them back and get rid of the negative if I really wanted to. Right?
Is it also possible to take out the 1/2 and put it in front so we don't have to do any of that?
Sure. Well, you mean any of what? The 1/2?
Any of the integration by parts?
Well, I'm not integrating by parts.
Or, oh.
There's no integration by parts because there's no multiple functions of y. So I could reverse them again, but we'll see. We'll see what happens. I may end up, not needing to. Who knows? Okay, so what happens when I integrate this thing? This becomes negative 1/6 u cubed, right? Evaluated from 0 to 1 minus x. Okay, so what does this become? This becomes, okay, plug in 0, we get nothing. Plug in, so this is 0 minus 1/6 times 1 minus x. Minus, this is a minus, so it becomes positive either way. Minus a minus, so this is cubed, right? Okay, and so now this is the integral on z on y, and we're just left with, I'm kind of veering here. Let me rewrite this so I'm not veering off the side of the page. Okay, 0 minus negative 1/6 times 1 minus x cubed. Okay, so that's just 1/6 times 1 minus x cubed. Integrate that from what? From 0 to 1. Oh, okay. dx. Boom. So this just becomes now a normal integration with respect to x. Okay, so we have 1/6 of, okay, the integral, okay, from 0 to 1 of 1 minus x cubed, okay, dx. Pull out the 1/6. Okay, and then we're going to do a u substitution again. Okay, so what was the last one here? Oh, it was blue. It was blue. This should all be in blue, but whatever. Okay. 0 to 1, right? Of this guy here. Okay, 1/6 1 minus x cubed dx. Okay, so now let's do a u on x. U is 1 minus x. So du is equal to negative dx. So it's basically the same thing we did before. Negative du is equal to dx. Okay, so 1/6. Okay, so what is this going to be? Well, again, this is going to be, if I plug in, if I do my limits of integration, if I plug in 0, I get 1. If I plug in 1, I get 0. So it's just 1 to 0 again. And this is going to be negative u cubed du. Oh, okay. Nice. So this becomes negative u to the 4th over 4. Okay, evaluated from 1 to 0 of 1/6. Okay, we'll plug this in. We're going to get 1/6 times 0 minus negative 1/4. That becomes positive 1/4, so the whole thing becomes 1 over 24. Oh, nice. Sweet. And that, my friends, is how you take a triple integral. Okay. Okay, let's see which one I want to do next. It's 420. Okay, so don't go there. Okay, so Let's just do the application. Okay, if I have time to go back and do some of these that don't have application, then I will, but let's just do the application. Okay, I don't want to sit here and just do all of the rote stuff and not get to the application part of it, if that makes sense. So, okay, and how are we going to apply this stuff? We're going to apply this with center of mass. Okay, remember we had a center of mass of a lamina before? Now it's center of mass of a solid. Center of mass of a solid. Interesting. Nice. Okay, so let's look at the center of mass of a solid. Okay, I want my red one. Okay, center of mass of a solid, right? Because we got some engineers in here. We don't need to do all the rote mathematics, you know. I mean, I apologize to the math majors, but you know, I want to make sure we get to we have enough time. Okay, there's more material that I can cover. There's more material in this class than I can actually physically cover in 16 weeks. Okay, so it's just, it is what it is. Okay, so it's hard. Okay, center of mass, X bar, Y bar, Z bar this time. Okay, center of mass. Okay, is equal to, okay, the moment, okay, of, with respect to YZ over M, with respect to the mass, okay, the moment of XZ with respect to the mass, and the moment of XY with respect to the mass. Okay. So we have those centers, or those moments. Okay, so this is the moment about the x-axis. This is the moment about the y-axis. Okay, the moment about the x-axis, moment x-axis, moment about the y-axis, and this is the moment about the z-axis. Okay, so instead of doing a double integral to find the center of mass of a lamina, right? Remember that surface or whatever it was, that two-dimensional. Now we're going to do a center of mass of a volume, okay? Of a volume, okay, where, okay, the moment about the x-axis, MYZ is equal to the triple integral. Okay, this is a triple integral E, okay, of x rho of xyz dv, okay, m of xz equals E y moment of xyz dv, okay, and m of xy equals E of z rho xyz dv. Okay. Okay, so those are the moments, and then also m is just the triple integral without, right? Without. So on z is z, we have the z, and then we just have without any x, y, or z. It's just with respect to the density function without any extra variable here is that. Okay, so to find this problem, guess what? Instead of 3 double integrals, we have to do 4 triple integrals. Isn't that awesome? Aren't you glad you came to math class today? You're like, you know what? I feel like doing 4 triple integrals to do one problem today. I knew that was what you woke up for this morning. You're like, you put your slippers on, you brush your teeth, and you're like, you know what I really feel like doing today? 4 triple integrals to do 1 problem. That's just going to make my day. I know it is. I know that's what you thought when you woke up this morning. Okay, that's why I didn't tell you. Otherwise, you wouldn't have come to class. Okay, so just exactly. Okay, I mean, I'm lucky I'm here. So, okay, number 5. I have incentive to be here. I get paid. So, what are we on? Example 2 or 3 or 3? On example 3, I think. Example 3. Okay, nobody laughs at my jokes. It must be Monday. Nobody's laughing at my jokes but me. That's okay. That's fine. I'll just laugh at my own jokes. Say, people ask me what I do for a living, and I say, I get to talk to myself all day. Yeah. They think I'm crazy. And maybe I am. There's like, you do what? Yeah, I said I sit in a room and talk to myself all day. And I get paid for that. They're like, COVID has made you go nuts. I understand. So, and then they back away a few feet. So, exactly. Okay. Again, nothing. No lulls. Can you just give me a pity lull? Can somebody please? Just so I know you're awake. Thank you.
I'm in shock that we're still doing this.
Thank you. Okay, there we go. That's good. Okay, good job. Okay, thanks. Thank you, Omar. Okay, it really wasn't that funny, but I do appreciate the pity laugh. Okay, I appreciate the pity LMAO. Thank you. That's good. Okay, some people are still awake. Okay, and get off Facebook and pay attention to me. Okay, that's all I'm gonna say. Okay, Facebook will not save your soul. Okay, focus. Okay, so find the center of mass, okay, of the solid of the constant density rho. That's nice. They give us a constant density. That's good. Triple integrals, Facebook. 4 triple integrals. That's good. Okay, thank you. Okay, so yeah, there you go. Yeah, everybody will unfriend you, Ashley. Okay, you post that on your feed, okay, you will lose all your friends. Trust me. I speak from personal experience. Okay, just don't do that. Learn from my mistakes. Okay, they'll run and hide, and you'll have no friends like me. Okay, so okay, find the center of mass of the solid of constant density. Okay, rho, bounded by the parabolic cylinder. Okay, x equals y squared, and the planes x equals z equals 0, and x equals 1. Okay, so we've got this parabolic cylinder, x equals y squared. What does this parabolic cylinder look like? Well, it's x equals y squared, right? X equals y squared, okay. So if this is x and this is y, then, you know, if you're thinking of x versus y, this would kind of look like the square root, positive and negative square root function. But it really looks like this, if you're thinking in terms of just y squared, right? So it's this parabola. Okay. Right. Okay. So that's nice. And then it goes where? It goes out to x equals 1, right? X equals 1. So it's bounded by this plane, x equals 1. Okay, it's bounded by the plane z equals 0, so that's the bottom. Bounded by this cylinder, and the planes x equals z. Well, where the heck is the plane x equals z? Well, if x is 1, then z is 1, right? When x is 1, z is 1. Z is 1. Okay, so x equals z. So x equals z. If x is 1, then z is 1. Okay, so let's think about this for a second. Let me do a little aside here, because I really want to understand, well, what does x equals z mean? What is that plane? Is that this plane here? X equals z? No. Is it? Oh, it's this plane here, right? The x equals z plane? Does it look like that? X and z are equal always? Something like this? X and z are always equal, but what? But x is bounded by 1. So the highest this thing can go up is 1. Okay, so it seems like it's, if we start at 0, 0, then we go up. It's going to be hard to draw. How do I draw this? I'm going to draw this like, I'm going to draw it a little bit slanty-ish. Okay, I'm going to draw it a little different perspective. Let's make this guy white. Okay, so a little bit different perspective. Okay, so got this guy here, right? And then at 1, when z is 1, I'm also at 1. Okay, so we've got, but it goes down. It goes down. It's hard to draw. I apologize for my sketchiness here. It's really hard to draw, but it's slanting up toward us. It really is slanting up toward us. If you think about it, it's like a slice of cheese, but the cheese is a wedge that goes toward the xz plane. Again, it's really hard to visualize here. Okay, but it's like a cheese wedge. Okay, it looks like this if I were to not use that perspective. Maybe a different perspective would be better. Okay, so I have my rectangle. And then I have my point out here. And we've got this like this. And then we've got this like that. Well, that's nicer. Okay, does that make sense? Does that help with the perspective? Hopefully. Okay, because this would be the line x equals z. Okay, thank you, Jose. Okay, so that's yeah, my chicken scratch here on the other one wasn't so good, but just think of it as like a cheese wedge, but it's a rounded cheese wedge. It is a cylinder. It's just it's sliced like I cut the cheese. I guess I shouldn't say that. Actually, that pun intended. So on that one. So I usually give myself like a half a second before I say something as a buffer. I've learned that in life. I give myself a half a second. I'm like, do I really want to say that? And then I just say it anyway. So, and it's whatever. Okay, so there we go, like so. Okay, so that's the cheese wedge, right? Okay, so we want to set up a triple integral for this thing. Okay, so what is z going from? Well, doesn't z go from 0 to whatever x is? Doesn't z go from 0 to x? Like isn't x equal to z? So z is equal to x, right? So it's going here, okay. And then, okay, So we really just want to look at what's our triple integral going to look like, right? What's our triple integral going to look like? Okay, so z is going to go from 0 to x. So that's dz. Okay. Okay, what's y going to go from? Well, we have this guy here that looks like this. So I really don't want to do y next, right? I don't want to do y next. I want to do x next. I want a function of x in terms of y. I want to do x next. Why? Because it's x equals y squared, right? If I did a function of y, if I did a function of x in terms of y, then I would have to do two different functions here. But if I do a function of getting reversed, a function of y in terms of x, okay, now I said it, a function of y, no, yeah, in terms of x, but I want a function of x in terms of, no, I don't. I'm going to get rid of the functions, okay? The function is just not, this is really what I'm saying, okay? I'm saying, look, I do not want a function of x, okay? I don't want that. I want a function of y. And so if I do a function of y, okay, where y is my variable, right? I don't want this to be the square root of x plus or minus. Okay, I want it to be a function of y. And if I do a function of y, then that means that my x's are going to, or sorry, my x's are going to go where? Well, they're going to go
I think your mic is muted.
okay, is that better?
Yeah.
Okay, sorry about that. Okay, so think of this as it's going to be a horizontal slice instead of a vertical slice this time, right? So 0 to x, and then, right, and then what's that's the z's, and then what's the y's? What are the y's going to go? Or sorry, what are the x's going to go from? The x's are going to go from y squared to 0. Or no, sorry, to 1. Sorry, 1. Okay, because x equals 1 is the top there. And then what's the y going to go from? dy. What's the y going to go from here? Well, the y is going to go from negative 1 to 1, right? Negative 1 to 1, right? On the negative 1 to 1. Makes sense? Okay, we're going to slice it horizontally, but we're going to add up all those slices. We're going to sum up all those slices. Right? So we're going to go from negative 1 to 1. Okay, so this is going to be z. And then what is this? Well, depends on what we want to plug in here. Depends on what we want to find. If we just want to find the mass, then we would just put rho, right? So if we just want to find the mass, we just put rho. If we want to find the moment about the x-axis, we put x. If we want to find the moment about the y-axis, we put y. If we want to find the moment about the z-axis, we'd put z. Okay. So we're gonna do this. Okay. We're gonna do our 4 triple integrals. Let's just do this one first. This one's going to be what? This one's going to be rho z from 0 to x. Okay, so that's going to be rho x. Okay, and then we want to do with respect to x. So this is going to be rho x squared over 2 from y squared to 1. Evaluate from y squared to 1. Okay. So, sorry, if I'm skipping steps, I'm just doing so because I want to try to save some time, but it's okay. Okay, so 1, right? So what is this going to be? Plug in 1 for x is going to be rho over 2 minus y to the 4th over 2, right? Sorry, rho y to the 4th over 2. Yep, I could factor out the rho over 2. Okay, rho over 2. I don't know why I'm using rho here. Just use p. I can't draw rows worth beans. They end up looking like e's. So there. Okay, so it's just going to be p over 2 times 1 minus y to the 4th. There we go. And then what are we going to do? Well, we're going to integrate the last one with respect to y. So this is negative 1 to 1 of p over 2 times 1 minus y to the 4th dy. Okay, so this is p over 2, negative 1 to 1 of 1 minus y to the 4th. So let's integrate that. That's just going to be y minus y to the 5th over 5, evaluated from negative 1 to 1. Okay. Cool, cool, cool. 1 minus y to the 4th, that has some symmetry about it. So we could have actually just kind of doubled what we're doing, but it's all good. It's all good. We'll get there. Okay, so plug in 1 here. So rho 2 times, I'm going to do a bracket. I'm going to pull that rho over 2 way outside. And I get 1 minus 1/5, which is 4/5. Okay, minus negative 1 minus negative 1 to the 5th power over 5. Okay, so what's this going to be? This is going to be, this is going to be 4/5. This is going to be negative 1 minus negative 1 over 5. So that's negative 1 plus 1/5 plus 1/5 minus, right? So we've got rho over 2. Okay, and so this is 4/5 minus, this is going to be negative 1 plus, this is going to be positive, oh, this is going to be positive 4/5 again.
Professor, isn't it negative 4/5 since it's negative 1 plus 1/5?
Yeah, but then you have to distribute a negative, don't you?
Okay, yeah, sorry, didn't notice that. Sorry about that.
Sure. Thank you. Thank you, Gregorio. I mean, it shows me you're paying attention, which is good. Thank you. Okay, so this is going to be 8/5 rho over 2. So that's 4 rho over 5. Okay, so that's 4 rho over 5. That's whatever the density function is times 4/5. I'll just do 4/5 rho. 4/5 rho. Boom, that's m equals m. Nice. Okay, 1 down, 3 to go. Woohoo. Yeah. Keep going here, right? Okay, so I'm not going to do all 3 because to me, that's kind of a waste of lecture. If you want to do all 3, the next 3, you can do it on your own and prove that this is true. Okay, so if I were to do m of yz, okay, I would get negative 1 to 1, y squared 1. Maybe we'll just do 1 for fun, for kicks and giggles. We'll do 1 for fun. Okay, we'll see how this works out. Okay, and then okay, 0 to x of x, right? Wouldn't this be x and extra x? X rho, which I'm going to use p dz dx dy. Okay, let's do this real quick. Okay, so this is going to be xzp from 0 to x. Plug in my x, that's x squared p, right? Let's take the integral now with respect to x. This is x cubed over 3p. y squared 1. So this is going to be x cubed 3, 1 minus y squared. Okay, and then I'm going to take that guy, that bad boy, negative 1 to 1 with respect to y. Okay, so I could, oh no, no. Screwed up already. Okay, this is what y squared, blah, blah. Okay, so this is dz. This is dz. And then I did dx. Okay. Did I screw up already? Okay, dx with respect to x, boom, plug that in. Nope, that's right. And then, oh, no, I screwed up. I did screw up. Okay, this is 1 minus, this is 1 cubed minus 1 cubed over 3. I'm going to put the row on the front. Minus y cubed, y squared cubed over 3. There, that's why I messed up. Okay. dy, right? So this is going to be, look at the 1. That's 1 cubed, 1/3. So this is 1 minus y to the 6th, p over 3, negative 1 to 1 dy. Okay, yes, I like what I've done there. Okay, so what is this? This is going to be y minus y to the 7th over 7 from negative 1 to 1, p over 3. Okay, cool. Okay, so this is going to be 1 minus 1/7, which is what, 6/7? So that's 6/7 plus another 6/7 for the same reason that we did last time. Okay, so that's 12/7 divided by 3 is going to be 4p over 7. Okay, so that's m y z. Okay, so then what would be x bar? What would be x bar? X bar would be this thing, 4p over 7, all over what we found to be our mass. But what was our mass? Our mass was 4p over 5. Oh, okay. So 4p over 5. So then the 4p's cancel, multiply by the reciprocal, and we get 5/7. Oh, look at that. That's nice. The other ones are going to be 0. Okay. And the last one is going to be 5/14 because, well, m of xz is equal to 0, but m of xy would have been equal to 2p over 7. Okay, so that's going to get me half as much, and half of 5/7 is 5/14. Okay, and so this is my center of mass. My center of mass there. Okay, good times. Good times. Again, I did skip over these two, but you can easily convince yourself of that by doing the integrals. The integrals are not that hard. Okay. Okay, let's move on to 15.7. Okay, triple integrals in cylindrical coordinates. I mean, these topics, they're just, I don't know, they're amazing topics. Okay, can you believe that we're almost done with chapter 15 and that we only have one chapter left for the entire semester? And that's kind of interesting. I mean, this is, it's winding down, people, winding down. Okay, 15.7. Okay, triple integrals in cylindrical coordinates. Triple integrals in cylindrical coordinates. Okay, so cylindrical coordinate conversion. You remember cylindrical, are we talking about cylindrical coordinates? Maybe not. Cylindrical coordinate conversion. Okay, what does it mean to be in cylindrical coordinates? Okay, in 3 space. Okay, it means that we have an X and a Y and a Z, right? An X and a Y and a Z. And where is this position in 3 space with respect to a cylinder, right? Where is this in respect to a cylinder? Well, if we look at the XY plane, then let's say that it's right here. Let's say that point right there, right? And say this is R. Then how far out do we go? Well, this is the X coordinate is R cosine theta. The Y coordinate is R sine theta, right? So R cosine theta. And then what are we doing? We're just going to go up to Z. Boom. Okay, cylindrical coordinates conversion. Okay, cylindrical coordinate conversion. Okay. Okay, and then the same polar coordinates, right? Cylindrical coordinates is basically polar coordinates just with your extra Z coordinate. So, you know, so we also have the same R squared is equal to X squared plus Y squared, and X is equal to R cosine theta. Oh, the inverse tangent of theta, or sorry, theta is equal to the inverse tangent of Y over X. Inverse tangent of Y over X. Okay, so let's see how this works out for us. Okay, number 1. A solid E lies within the cylinder X squared plus Y squared equals 1. And below the plane, Z equals 4. Okay, so below the plane, Z equals 4. And above the paraboloid, okay, above the paraboloid, Z equals 1 minus X squared minus Y squared. Okay, the density at any point, okay, at any point is proportional to its distance from the axis of the cylinder. Okay. To its distance from the axis of the cylinder find the mass of E. Mass of E. Okay. Okay, so what does this mean that the distance, that the density is proportional to the distance to the axis? Well, what is the distance to the axis? The distance to the axis here. Well, let's look at what's going on here. Okay, we're saying that this lies within the cylinder X squared plus Y squared equals 1. Well, what is that? That's the unit circle, but just it goes infinitely in the z direction, right? Okay, that's infinitely z direction. Boom. But it's saying, hold on a second. Okay, hold up a minute. Okay, so not that. We're going to top it off at z equals 4. Okay, so this is at 4. Okay, so it's like, hold up a minute. We're going to top it off at z equals 4, right? Okay, z equals 4. Boom. Okay, so what is the density? The density is going to be proportional to the distance to the center, right? So Kr. I'm just going to say some sort of proportionality constant from how far away, how far out it is, right? So say that we had this point here. Well, that's going to be the density is proportional to how far out the radius is. Even if we were up here, it would still be how far we are from the axis, you know, from the axis of the cylinder, right? So R, okay, RDRR. Okay, so that's what rho is. Rho is, okay, KR, okay? Okay, so let's find the mass of this thing. The mass is going to be my triple integral, okay, in cylindrical coordinates. But what is cylindrical coordinates? Well, it's just polar coordinates with an extra z added on, right? So this is going to be KR times dz dr d theta, okay? dz dr d theta, that's cylindrical coordinates, okay, in terms of a triple integral, okay? So actually it's not, I lied, okay? It's not. What did I do? I did a cardinal sin here. It says r dz dr d theta, okay? Don't forget the extra r, okay? Because if we have this guy here, okay, because rho really was in terms of x, y's, and z's. Okay, that's where I screwed up. It was in terms of x, y's, and z's, and so we have this guy e of x, y, z dv. That's going to go to, okay, to a triple integral, okay, in terms of f of r cosine theta, r sine theta z of r dv dz dr d theta. That's, and then what is this going to go from? Well, this is going to go from some sort of you know, u1 of r's and thetas involving r's and thetas. Z is going to go from, z is going to be in terms of r's and thetas, and then this is z is going to be in terms of r's and thetas. This is a function of r's and thetas. Okay, and then what's r going to go from? Well, that's a function of theta. Okay, so we would say this is, you know, h of theta 1 to h of theta 2, or we should actually say h1 of theta to h2 of theta. Okay, and then what's theta going to go from? That's going to be a function in terms of thetas. And then what's theta going to go from alpha to beta? Okay, alpha to beta. So that's how we are going to, okay, translate this thing. Okay, so let's see how we can move this from, okay, from x, y's, and z's to r, z, r's, and thetas. Okay, z, r's, and thetas. Okay, so what's z going to go from? So this is actually kr squared, right? Okay, what's z going to go from? Well, z is going to go from, okay, this guy, this is going to be on the bottom, to 4, right? And what does this look like? Well, let me draw this a little bit better. This is going to be, when x is 0 and y is 0, this is going to be 1. So if this is 1, it looks like this. This is going to be the top of this dome here, this parabolic shape here. Okay, make sense? Actually, it doesn't make sense like that. Get rid of that. That's really bad drawing. Okay, so it's going to be, get rid of the axis. It's going to be the top of this dome here. Okay, and so looks like that. Okay, and so what's the volume that we're really looking at? We're really looking at this volume here. Okay, that's above this. It's kind of like, back, you savage. There you go. There we go. Okay, so okay. So we have this thing here, right? Does that make sense? Okay, so what are the slices? What are the slices of z going to go to? Well, they're going to go to from the top of this dome to 4, right? And what is that? What's the equation of that dome? What's the equation of this dome here? Okay, what's the equation of that dome? Well, it's z equals 1 minus x squared minus y squared, right? From that up to 4, right? Okay, but here's the big but. But what is this thing in terms of r's and thetas, right? Because we want dr d theta. Well, isn't x squared plus y squared equal to r squared? So I don't want just this. I want this in terms of r's and thetas. So that's 1 minus r squared. Oh, okay. So because z equals 1 minus x squared minus y squared, factor out the negative, this is x squared plus y squared. So z is equal to 1 minus r squared. 1 minus r squared. Right? In terms of r's and theta. So this is z of r is equal to 1 minus r squared. Or we could say z of r theta. There just doesn't have to be any theta in this. Okay, so z goes from 1 minus r to 4. Okay. So what about r? What does r go from? What is r? Well, r goes from 0 to 1, right? 0 to 1. R goes from 0 to 1. Okay, that's what r goes from, 0 to 1. And what about theta? What does theta go from? Theta goes from 0 to 2 pi, right? Okay, cool. Now, we're just going to integrate. Okay, so this is going to be kr squared z from 1 minus r squared of 4. Okay, so this is going to be, plug in, we've got 4k r squared, okay, high resolution r squared, okay, 4k r squared minus, okay, k r squared times 1 minus r squared. Okay, this is dz, right? We integrated with respect to z. Is that right? Or did we not? Yeah, we did. We did. Okay, with respect to z. Okay, so this becomes, I'm going to factor out the r squared maybe? No, I'm going to leave it in. Okay, so this is 4k r squared minus kr squared plus kr to the fourth. Oh, okay, that's cool. So this becomes 3kr squared plus kr to the fourth. Okay. And then this just becomes, stop. I could pull out the k if I really want to. K is just my proportionality constant. Okay, this just becomes a regular polar coordinate problem. So r goes from 0 to 1 and 0 to 2 pi of 3r squared plus r to the fourth, dr d theta. Oh, okay. Okay, so k, this is going to be 3r cubed over 3, which is r cubed, plus this is r to the fifth over 5, so from 0 to 1. Okay, so plug that in, that's 1 plus 1/5. That's 6/5. So 6/5. 6/5, okay. Integrate from 0 to 2 pi of theta, so that's k. This is going to be 6/5 theta from 0 to 2 pi. Plug in 2 pi, that's 12 pi over 5 times k. Boom. Okay, and that's the mass. Mass is equal to that, depending upon whatever my proportionality constant is. Okay. Okay, let's do one last one here, since we're having so much fun. So much fun. Okay. If this class was offered asynchronously, would you guys have taken it? Like, or do you I mean, personally, I would be like, it would be really hard for me to teach this stuff to myself. No. I mean, there is a benefit to having a live professor, right? Like, I mean, you have to have somebody work this stuff out for you, I think. I mean, I think that it's just a level of difficulty. I mean, you can't just sit there and watch Khan Academy and maybe teach yourself. I mean, you could, I guess, teach yourself anything, but I mean, it's really hard. I mean, has anybody taken an online course where it's just like you just check in weekly? Yeah, I mean, it's just, to me, that just seems very difficult. Okay, definitely helps. Okay, good. Yeah, I'm just thinking. Okay, I'm just brainstorming. Like, it's 10 times better. Yeah, to me, it's this. It goes this, and I've learned at all levels. Okay, I've taken all levels of classes, all right. So to me, it looks like this, right? It's kind of like a hierarchy. Like, what's best? This is best, and this is not so best, not best, right? So in mathematics education, I think there's 4 levels. Maybe in other education, there's 4 levels, right? So this is, the best is face-to-face. Face-to-face. The next one is, you know, live remote instruction. Okay, and then this is asynchronous instruction. And this is what we used to call correspondence, which is basically correspondence is basically you're just learning from a text and you're sending in you would mail in your work. There's no, like, there is zero there's zero interaction with you and the professor. Like, this is the worst. Okay, I have taken the correspondence class. I've even taken one in math. That was how I studied to get my actuarial license. So I had to take all of these tests and study remotely. They basically just gave you a book and a study manual. Here you go. Teach yourself high-level mathematics. It's like master's level mathematics. So just teach yourself. Like, not everybody can do that, right? So does this make sense? Like what I think is like, right? So basically this is just, you know, teach yourself out of a book. This is teach yourself with YouTube, I think. Right? So teach yourself with YouTube. Teach yourself with a book. Teach yourself with YouTube. This is teach yourself with live instruction. Okay, this is actually professor. Okay, and then this is teach yourself inside a class. So I think that's best. Okay. Unfortunately, we can't have this right now. Okay. I mean, we can maybe next semester, but we'll see. Let's see what happens. Okay. With the state. Okay. My kids are back in school. They went back to school last week. That was kind of cool. 50% of the time, but at least they're back. You know, I have a high school junior and a high school senior, and I was like, I need to get them the hell out of the house. Okay, that was my goal. My goal was not their education; it was get them the hell out of my house. Okay, so that I can actually do a dish without it piling up again. Okay, 5 seconds later. Right, like, you know, they say, what is the definition of insanity? Trying to do housework with a 3-year-old. Yeah, in the house. That's the definition of insanity right there. Okay? It's like trying to do housework in a tornado. It's not gonna happen. It's like, I just picked this up. Just picked this up. Okay, could it stay clean for like 5 minutes? 5 minutes. That's all I'm asking. 5 minutes. But no. So, but I admit that I probably am a failure of a father, because yeah, exactly, because I was like, the problem is the older one is a boy, and he doesn't get it. He doesn't like I don't know. He's like I'm like, could you pick up a dish? Like, and he's like, why? What's in it for me? I'm like, you see this sandal here? I'm just kidding. So it's like the sandal might be coming your way in a second if you don't pick up the dish. But I don't know. He's going to be 18 in 3 months. I don't know. I don't know if I have thoroughly prepared him for the real world at this point in life. And that has been my failure, I guess, as a parent. But he's in for a big wake-up call at some point, because I'm not going to support him until he's 45. So there you go. So he will be. Yeah, exactly. I mean, they have, both my kids have their own money. I mean, he's a saver. He's saved up like over $1,000 right now in his account. He'll get more for Christmas and birthdays or whatever. And then I told him as soon as he turns 18, he's going to get a job, or I'm going to kick his ass out. So I'm like, that's it. Like, you go get a job, or you go mooch off with someone else. So I'm a single dad raising 2 kids on my own. So I can't have a slacker after 18 years old. And he realizes that, I hope. So, you know, and I've been at this, you know, single dad thing for over 10 years. So I was like, there is a day of reckoning coming for both of my children. My daughter picks up, so she helps. But he I don't know. We'll see. We'll see what happens. He's a good kid though. He gets really, really good grades. So like, and he's never like, he doesn't get into any trouble. So it's hard for me to say, you know, like, oh yeah, you should pick up a dish once in a while, when, you know, he's pulling, you know, really good grades in high school and has, you know, really good friends and stays completely out of trouble, you know, no drugs, no sex, no nothing. So I count my blessings, you know, so, but yeah, I mean, if those are my troubles compared to what other parents have to deal with, I'm pretty lucky, I think, at this point. However, teenagers, I don't get it. I don't know. Yeah, exactly. Nobody's pregnant. Nobody's gotten anybody pregnant. So I'm doing okay. Yet. Okay. I think they know that if that happened, their ankles would be broken. So, you know, they couldn't be in a relationship anymore because they would be in a wheelchair. So I'm just kidding. That's a joke. Okay, that is a joke. Okay, that's me joking. Don't take this stuff seriously. Okay, I've never laid a hand on my children. Frequently. Just kidding. There you go. So. Single mothers, yeah. Well, single fathers. You know what? I think it's harder to be a single father because you don't get any like you don't get any pity. Nobody pities you. Like I don't want any to be pity, but like you know, you throw me a couple $100 once in a while, I'd be pretty happy. You know, I don't think we get. I don't know. It's kind of like oh, that poor single mom. They don't say, oh, that poor single dad. You know, it's like, well, he's just doing what he needs to do. Don't put your big boy pants on. Right? There you go. Anyway. Whatever. Okay. Have them do triple integrals. There you go. Exactly. Let's do one last one, shall we? Let's do one last one. Okay. Put our big boy pants on, our big girl pants on, and do some triple integrals. Exactly. Okay. So number 2. Okay. Evaluate. I'm going to make this a thinner line here. Okay. Thinner line. Heck, if I can do this stuff, anybody can do this stuff. Come on. So. Okay, let's evaluate the following. Okay. I'm going to set this up for you. This comes from this here. Okay, so this is our cone, right? This is the cone. Okay, in 3 space. Okay, so this is a cone in 3 space. I'm going to make the radius of this cone. Okay, the radius of this cone. Okay, it's going to go from, it's going to be a circle. So if we were to look at the projection of this in the XY plane, okay, this would be a circle of radius 2. So this is going to go out 2. Okay, so this is going to go out 2. We want to find the triple integral here. Okay, so triple integral of this thing. Okay, and the triple integral of what? Well, we're going to take x squared plus y squared. We're going to go dz, dy, dx, and we're going to say that x goes from -2 to 2. Okay, x goes from -2 to 2. Okay, which makes sense. -2 to 2. Okay, y goes from what? Y goes from negative square root of 4 minus x squared to positive square root of 4 minus x squared. Okay, z is going to go, this is a cone. This is going to be the bottom of the cone to the top here, z. And so z is going to go from, this we're going to have be at 2. Okay, so the height here is going to be 2. These are all 2s, 2, 2, 2. Okay, so the height of the cone is 2, whereas the slant of the cone, the slanted side, is the actual function of the cone. And what is that going to be? That's going to be z equals, okay, the square root of x squared plus y squared. That's going to be the top half of this cone. Okay, we could have the bottom half as well, and then it would be plus or minus, or it would be z squared equals x squared plus y squared. This is the top and bottom. This is the top and bottom of the cone. Okay, but this is just the top half. of the cone there. And so it's square root of x squared plus y squared. Okay, so notice all these x squareds and y squareds and these you know, this is a quadric surface, which really lends itself to okay. It really lends itself to putting this into polar coordinates, or in 3 space. It's cylindrical coordinates, right? Cylindrical coordinates. Okay, so let's translate all of this stuff into cylindrical coordinates to make the integration a whole lot easier, because I don't want to have to deal with these square roots of x squared plus y squared if I don't have to. That's just going to be a nightmare. Okay, so what is this going to be? Okay, so let's think about how are we gonna do this. This is z equals, okay, what's z going from? Z is going from this guy here, okay, the bottom is z equals the square root of x squared plus y squared. But what is x squared plus y squared?
R squared.
R squared, thank you. Thank you, Calixto. Okay, so R squared, what's the square root of R squared? Isn't that just R? Okay, or basically absolute value of R, right? So in this case, we're just going to make it R. Okay, we don't need to make it the absolute value of R. Okay, just because we want R to go in the positive direction. We don't need it to go in the negative direction. Okay, so z is equal to R. So that's kind of nice. So the integral here is going to be from R to 2 of what? Of x squared plus y squared. That's R squared. R squared. R, don't forget the R, right? Don't forget the R, because we're changing from rectangular to polar. R dz dr d theta. Okay, so now what does R go from? What's R going from? Well, this is a circle of radius 2. So isn't R going to go from 0 to 2? Yeah. This in the xy plane. This is x squared plus y squared equals 2. Okay, or R squared. Or sorry, this is 4. Okay, or R squared is equal to 4. So R is equal to 2. Okay, so this goes from 0 to 2. Okay, and then what's theta go from? It's all the way around. So it's 0 to 2 pi. Okay, well, this is easy. This is R cubed dz dr d theta from R to 2. Okay. From R to 2, 0 to 2, and 0 to 2 pi. Okay, and so this is going to be R to the 4th over 4 from R to 2. Okay. Okay, and then 0 to 2 and 0 to 2 pi. Okay, the r d theta, right? Okay, so plug in, wait, I did this wrong. My bad. I don't know what I'm thinking. I need to integrate it with respect to z, not r yet. So this is going to be r cubed z. Okay, sorry about that. Okay, from r to 2. Plug in 2. This is 2r cubed minus r to the 4th. Okay. Evaluate it from 0 to, there I go sideways again. Okay, evaluate from 0 to 2 of, what was this? This was 2r cubed minus r to the 4th, dr d theta. This is 0 to 2 pi. Okay, and so then we're going to do what here? We're going to now we take the integral with respect to r. So this is going to be 2/4 r to the 4th minus 1/5 r to the 5th from 0 to 2. Okay, so this is, we're going to plug in 2 here. So this is going to be 2 to the 4th over 2, which is 2 to the 3rd. So that's 8. Minus, this is 2 to the 5th over 5. That's 32 over 5. Okay, and then you plug in zeros, it just goes to 0. then this is 0 to 2 pi d theta. So 8 minus 32, that's 40 minus 32, that's 8/5. So this is 8/5. And then integrate that, that's theta, evaluate from 0 to 2 pi. That's 16 pi over 5. Boom, that's it. Done. Okay. I did skip over an example today, but I think we're okay. Okay, I think once we start talking about the polar, I think we're good. So, okay. Well, maybe we'll do. Can we do one last one real quick? I don't know. Let's find the volume real quick. Okay, what happens if we want to find the volume of something? Okay. Let's do what are we on here? Let's do the last one here. It's very real quick. Let's call this number 3. Number 3. Find the volume. Okay. Of what? Find the volume under this thing real quick. So find the volume under the tetrahedron. Let's find the volume under the tetrahedron that we did earlier. Okay, find the volume under the tetrahedron from, I think it was example 2. Right? From example 2. And so what was this? Well, if I want to find the volume, okay, using a triple integral, then we let our function equal 1. Okay? To find volume, let z equal 1, or we'll say f of x, y, z equal 1. Okay, it's the same thing, again, that we have done before. When we want to find distance, we let the integral equal 1. When we want to find area, we let the double integral equal 1. When we want to find volume, we let the triple integral be of 1, right? So again, distance is 1 dx, distance. Double integral, let it of 1, dx, dy, dx, this is area. And the triple integral of 1, z, dy, dx is volume. Okay, I just want to make sure you guys know that. If you do a triple integral, okay, on 1, it will give you the volume of what? Well, this gives me the distance, okay, between my x values, okay, from a to b, right? Wouldn't this to be b minus a? The distance between b minus a, that's what that becomes. Okay, what's the area here? Well, the area is going to be whatever your area is, okay, on this you know, this guy here, okay, and that's going to go from, I don't know, we'll say h1 of x to h2 of x, and then x is going to go from a to b, okay, right? So that'll find our area. Here we're going to find, right, this is going to be a h of, say, xy, and then h of xy. Then this is going to be h of x, and then this is, or sorry, we'll do g of x, and then this is just x goes from a to b, right? Okay, so 2 variables, 1 variable, and then numbers. We always end in numbers. Okay, so that's the volume. Okay, so let's go back to number 2 and let's just see. Okay, we already have the setup for this tetrahedron, right? This 1, 1, 1 tetrahedron, right? And we want to know what's the volume of this tetrahedron. Right? What's the volume of this tetrahedron? Okay, so let's just say, oh, well, this is going to go from 0 to 1, 0 to 1 minus x, and 0 to 1 minus x minus y of 1. We had z there before. Now we just have 1. This is going to be dz, dy, dx. Okay. So let's see what we got here. This is going to be z. evaluated from 0 to 1 minus x minus y. So plug that in. That's 1 minus x minus y. Oh, okay. Okay, you integrate that from 0 to 1 minus x on y. Okay, so this, integrate this with respect to y. This is going to be 1, this is going to be y, minus xy minus y squared over 2. Okay, and then plug that in for 0 to 1 minus x. Okay, so this is going to be 1 minus x times 1 minus x minus 1/2 times 1 minus x squared. Okay, and then we're going to evaluate that, integrate that on x. Okay, dx here. Okay, so let's see what I can do here. Maybe I'll just multiply all of this out so I don't have to do integration by parts. Okay, so this is going to be 1 minus x plus x squared, okay, minus 1/2 times 1 minus 2x plus x squared. Okay, so this is going to be 1 minus 2x plus x squared, and this is going to be 1/2 minus 1/2 plus x, okay, minus 1/2 x squared. So, okay, right, we're still just multiplying this out. Okay, and then, so this is 1 minus 1/2, which is 1/2. This is negative 2x and x, which is minus x. And then this is x squared minus 1/2 x squared, which is 1/2 x squared. Okay. Integrate from 0 to 1 dx. Okay, so what is this going to be? This is going to be 1/2 x minus x squared over 2 plus 1/6 x cubed. Right, so from 0 to 1, evaluate from 0 to 1. Okay, so this is going to be 1/2 minus 1/2. Oh, that's kind of nice. Plus 1/6. So it's 1/6. The volume. So if you have a 1 by 1, if it looks like this, if you have a 1 by 1 tetrahedron, then what's your volume here? Your volume is 1/6 of a 1 by 1 by 1 cube. Kind of interesting. So again, we just have this slice here, and then this slice, and it's going right here, and it's going right here. So we're saying that this piece here is 1/6 of the entire whole cube, which if you sliced it up, you could actually probably slice it up into 6 equal pieces. You know, take your little Rubik's Cube. Where's my Rubik's Cube? Take your little Rubik's Cube. That's not the big one. Anyway, whatever. I would want the 3 by 3, which is in the other room, but you take your little Rubik's Cube here, and you could slice it up in such a way that you would get six equal tetrahedron in there. Cool? Good stuff. That was a good problem. I'm glad we went through that one. Okay? Okay, I'll see you guys on Wednesday.
Thank you, Professor.
You're welcome.
Thank you. Bye.
Hasta la vista, baby. You're welcome. I'm glad to serve.